Welcome to this explainer. Today we're diving into a highly requested topic, a classic challenge from computer science with Sir Bison. We're tackling a foundational problem, straight from the Cambridge A-Level Computer Science syllabus, specifically the October/November 2023 paper 32. If you've ever wondered how on earth computers actually manage to store complex negative decimal numbers, well, you're in exactly the right place. Let's break this whole thing down step by step so you can lock in those easy marks. Here's our roadmap for today. We'll start by tackling floating point representation. Then we'll convert the positive value, apply 2's complement, normalize the mantissa, calculate the exponent, and finally, put it all together for our 16-bit answer. All right, let's jump right into step 1, tackling floating point representation. First things first, let's establish our exact end goal. Our target today is negative 96.75. We need to convert this specific negative decimal value into a 16-bit floating point format. Now, the rules for this format tell us we absolutely must use a 10-bit mantissa and a 6-bit exponent. Just as a quick refresher, the mantissa holds the core digits of our number, and the exponent basically tells us where the decimal, or rather the binary point, belongs. So this brings up a really interesting question, right? How do computers actually process this? Because, we can't just feed a system negative 96.75 and expect it to know what to do. We have to map it out precisely into a strict binary format that fits within those exact 16-bit hardware constraints. Which brings us to step 2, converting the positive value. Honestly, the absolute best trick for dealing with a negative target is to just completely ignore the negative sign for a minute. Let's start with the positive version. First, we tackle the whole number, 96. If we use our standard binary place values, 64 plus 32, we get 110000. Next up is the fraction, 0.75, which is just a half plus a quarter, giving us 0.11. Finally, we stitch those two pieces together. But we have to make sure to add a crucial leading zero to represent that positive sign bit. So that leaves us with a positive representation of 0110000.11. See that leading zero right at the very front? That explicitly tells the computer, hey, this is a positive number. It's a super easy starting point, and it sets the perfect foundation for what we have to do next. Okay, moving on to step 3, applying 2's complement. Now that we have our positive binary sequence, we're going to use 2's complement to flip it over to a negative. The first step here is actually surprisingly simple. We just find the 1's complement by flipping literally every single bit. So zeros turn into 1's, and 1's turn into zeros. That transforms our positive binary into 100111111.00. But wait, we aren't quite done yet. To finish off the 2's complement process and really lock in that negative value, we have to add a 1 to the very end of our flipped sequence. When we add 1 to that final 0, we end up with our raw negative binary number 1001111.01. And there it is. That is the true binary representation of negative 96.75. Now for step 4, normalizing the mantissa. With that raw negative number secured, we need to format it properly for floating point storage. We do this by finding our balance and normalizing the mantissa. Now, normalization is just a strict formatting rule that ensures maximum precision within the computer's memory. The rule dictates that for a normalized negative number, the mantissa absolutely must begin with a 1, immediately followed by a 0. It literally has to start with the digits 1, 0. If it doesn't, well, it's not normalized, and we have to physically shift the binary point until it is. So the big question is figuring out exactly how far we need to move our binary point to satisfy that 10 rule. Looking at our raw number, to get the point right after that first 10, we actually need to shift it exactly 7 places to the left. Once we do that, we perfectly format our number as 1.00111101. And if we just drop the point, that gives us the 10 necessary bits for our mantissa, 100111101, which leads us right into step 5, calculating the exponent. We've got our mantissa, but we definitely can't forget about those 7 steps we just took during normalization. That movement is exactly what determines our exponent. Because we moved the binary point 7 places to the left, our exponent value is a positive 7. Just keep in mind, if we had moved it to the right, it would be negative, but shifting left always means a positive exponent. Now, do you remember our parameters from the very beginning of the explainer? We need a 6-bit exponent. So we just convert that decimal value of 7 into a 6-bit binary representation. The number 7 is just a 4 plus a 2 plus a 1. So in binary, that's simply 111. To make it fit our 6-bit requirement, we just pad it out with some leading zeros. And that gives us our final exponent piece, 000111. And finally, step 6, the final 16-bit answer. All right, we have done all the heavy lifting, so it's time to stitch this whole shebang together and get our final 16-bit sequence. Placing our 10-bit mantissa alongside our 6-bit exponent gives us the clean, undeniable final answer for negative 96.75. So we've got our mantissa on the left, 100111101, and our exponent on the right, 000111. When combined, this exact sequence of 16 bits is literally what the computer stores in its memory to perfectly represent our original decimal number. As we master these step-by-step conversions, it kind of opens up a broader, really practical question. What actually happens to binary precision if a number requires way more bits than the system allows? I mean, we got pretty lucky here, right? But consider the physical limitations of computer architecture. How might missing bits, just due to a lack of memory space, impact decimal accuracy in critical, real-world applications? Think on that. Keep practicing your 2's complement, and I'll catch you in the next explainer.